The second Q&A session is on mitigating hallucination in large vision language model via DPO on policy data of the key by J.U. Yang, Zhufang Liu, Donqi Han, John Jian Zhu, and Dongqin Li, and the paper will be presented by Ji.
Good morning, everyone. Thanks a lot for coming here. My name is Zhufang Yang, a PhD student from the Chinese University of Hong Kong, and this work is conducted during my internship at Microsoft Research Asia. And our topic is about mitigating hallucinations in large vision language models via DPO on policy data for the key. Before I get started, I just want to introduce some background about the hallucinations in large vision language model and existing solutions. So take the following figure, for example. We just asked the large vision language model to describe this image in data. But actually, it just counts the wrong number of the children and describes the wrong item they are playing with. So to mitigate such hallucinations in the generated response, people have already proposed two classes of methods. And we call the first class as the training-free ones, and the second class as the training-based ones. And generally, the second class introduces better results. And within the second class, reinforcement learning is the most common choice. That is, if we can find a reward function which can reflect the hallucination severity, then we can set up our initial objective as to maximize the reward function and at the same time constrain the KR divergence between the current policy and reference policy. But actually, the reward function is really hard to train or obtain. So based on this point, direct preference optimization just becomes the most popular and effective solution. Because it just transfers the initial objective to the following practical rules, which means that if we have the preference pair, then we can conduct the DPO training. So take the aforementioned case, for example, based on the same image and prompt, then we can construct the preference pair based on the severity of the hallucinations. So in this work, we just do the following three things. Firstly, we conduct a systematic review of DPO-based algorithms for addressing the hallucinations in large vision language models. And secondly, we identify the intrinsic property of DPO, specifically its high reliance on policy data. And lastly, we propose a new algorithm called policy alignment DPO. It is simple but effective, and achieves solid results with only 4.8 thousand data, and previous solid algorithm utilized 16,000 data. So as I introduced before, DPO-based algorithms is the most common choice for addressing the hallucination phenomenon. But actually, we find that their performance still varies a lot, and these variations mainly comes from how do they construct the preference pair during the DPO training process. So based on this point, we just summarize the aforementioned DPO-based algorithms in the following three classes. And we call the first class as a hallucination injection. That is, given an image and prompt, and also we have the ground truth response. Then we can ask GPT-4V to inject some hallucinations. Then during the DPO training phase, we can construct the preference pair between the ground truth one and the hallucination one. And for the second class, we call it the hallucination recognition. That is, given image and prompt, we ask the model to be trained to generate response accordingly. Then we can ask a human expert or GPT-4V to identify the hallucinations within this generated response. And after that, we can get a revised response. Then during DPO training phase, we can construct the preference pair between the revised response and the generated one. And third class, we call it the self-evolution. That is, given image and prompt, we ask the model to be trained to generate multiple responses accordingly. Then we ask the teacher model to rank these responses according to the severity of the hallucinations. So during DPO training phase, we can construct the preference pair according to the ranking results. It should be noted that hallucination may exist in both responses. So based on my above description, we can find that for method 1, the hallucinations are not from the model itself, so it should be least effective. For method 2, because we use precise feedback and corrections, so we expect it to be the most effective. For method 3, due to the dimensional disaster during the autoregressive generation process, so persistent hallucinations are difficult to eradicate. So we expect our experiment result has method 2 better than method 3 better than method 1. But during our experiment, we find that method 3 is better than method 2. So the question is, why facts conflict with our intuitions? That is why method 3 better than method 2. To understand this point, we need to recap the initial objective of the DPO training. That is, we have a clear divergence constraint between the current policy and reference policy. So take a close look at the definition of clear divergence. We can deduce the following fact. That is, if we can find a response whose probability with respect to the current policy is greater than 0, but its probability with respect to the reference policy is approaching 0, then the clear divergence between these two policies will go to infinity. And this property just tells us any off-policy responses can never be learned by any policy, starting from this initial objective. Using the following diagram to describe this relationship, that is, the support for the current policy is always a subset for the reference policy. So let's recap the method 2 hallucination recognition. In this revised response, because they are generated by human expert or GPT-4V, so we never consider about its probability with respect to the policy to be trained. So there are a few tokens whose probability will approaching 0, which means that they are off policy. And we can never expect the policy can be learned by using the DPO training. So a natural question is, what will happen if we use this off-policy preferred response to conduct the DPO training? To understand this point, we need to take a close look at the gradient of the DPO training objective. And we find it consists of two parts. And the first part, we call it the weight part. And the second part, we call it the gradient part. And the main difference comes from the weight part. Because initially, pi theta equals to our reference, so minus our weight plus our roots equals to 0. So the updating weight will equal to 0.1 beta according to the sigma function. But shortly after, because we just conducted several steps of the log likelihood maximizations on the preferred response, then our weight will go to extremely larger because the denominator in this form is approaching 0. So the weight will just go to 0. Then our gradient just vanish. So how can we fix this issue? Using the following diagram to describe this, we just expect our policy after DPO training to follow the distribution of the right object plot. But actually, the off-policy preferred response can never be learned. To solve this problem, I think the most simple way is to conduct a supervised fine-tuning on this revised response. So we will call it the on-policy alignment. And after this step, we'll get a new policy. We call it pi OPA. And based on this point, we can just conduct the following DPO training, and the problem can be solved. So let's take a close look at our methodology. We call it on-policy alignment direct preference optimization. So first step, giving image and prompt, we can ask the model to be trained to generate response accordingly. And after that, we can ask GPT-4V to identify the hallucinations within this generated response. And after that, we can conduct low-rank supervised fine-tuning on the ground truth response and this revised response. And after this step, we'll get a new policy, and we call it on-policy alignment policy. Please note that all these three responses with respect to this policy are on policy. And our DPO training will start from this point. And the last step is to conduct the DPO training. And we just form the 6 preference pairs. Please note that we have image focus mechanism and entry pairs sourced from the MDPO. But the most important thing is our on-policy alignment operation. So lastly, let's take a close look at our experiment results. We find that DPO is especially effective for the direct indicators about the hallucination rate. So we just plot some important metrics about this, just like the amber hallucination rate, objective sentence level hallucination rate, and the MML hallucination rate. Please note that all the metrics in this slide is the lower the better. And we just utilize 2 models as starting point, which are level instruct 1.57b and 13b. As we introduced before, method 3 evolution is the previous pseudo line, and the algorithm utilized method 3 is called RLAIFV. And to form the comparison, we achieved more sort of results on more benchmarks. And they utilize 16,000 data for training, and they tune the 4 parameters, and they conduct the DPO training for 4 rounds. But as for our OPA DPO, we just utilize 4,800 data, and we use low rank method to tune the model, and we conduct the DPO training for just 1 round. An important problem is how important the OPA operation is. To understand this point, we just conduct some ablation studies. As you can find, OPA operation can result in nearly 50% of decretion in the indicators about the hallucination rate. As we deduced before, use the policy preferred response to conduct the DPO training will introduce the gradient advantage phenomenon, and the following figure just verifies this point. And lastly, to understand the scalability of our method, we just study the impact of the data scales, as shown in this figure. As you can find, with only 600 training data, OPA DPO surpassed most algorithms in the hallucination-related metrics. And another interesting phenomenon we observed is that increasing the training data does not necessarily lead to the improvement of the policy after OPA operation, but increasing the training data will increase the enhance the performance of the policy after DPO training. So effective and efficient data is still necessary. That's all about our work. Thanks for listening.
Thank you. We have time for questions. Have you tried to do these 2 steps also multiple times, and did you observe any other improvement? I know that you compared to other methods that did DPO multiple rounds, and your method was 1 round was sufficient. But I'm curious if you tried this multiple rounds and if you may observe improvements.
Yeah, actually, if we do multiple rounds of DPO training, then we'll find some overfitting phenomena. So we just train DPO for 1 round. Yeah. Okay, thank you so much.